All right, good morning, everyone. I hope you all had a good first week classes. Looking forward to a cold weekend. So to begin, let me just remind you a couple of things. We have our start of term survey, which you need to finish by midnight on Monday. The link to the survey is on the Canvas page, the Phys 121 Canvas page. Homework number 1 on Prairie Learn is due Wednesday at midnight. That is just like an introduction to Prairie Learn. Homework, there's not really any physics content in there. And then homework number 2 is going to be due on Friday at midnight of next week. Okay, the other thing I wanted to mention that I forgot to mention on Wednesday is that Wednesday and Friday, I have, of course, this class 10 to 11, but then I have a class that starts at 11 right away. So Wednesdays and Fridays, I'm not going to hang out front here. So often people like to come up and ask questions just as class is ending. Unfortunately, Wednesday and Friday, I gotta leave quickly, but Monday, I don't have that class that's right after this one. So Monday, I'll be a little more available after the class. Okay, so what we were talking about was kind of a bit of a mini review of some Physics 111 topics. We were talking about a mass on a spring and then a pendulum, and we were trying to see if we could relate those two problems to one another. And the pendulum is one of the things you're going to look at in labs 1 and 2. Again, labs and tutorials, they're not this week, they're not next week, but in the third week. I think the week that starts January 22nd is when both labs and tutorials will start. Okay, so we thought about this mass on a spring. We wrote down Newton's second law, F equals ma, and then we did some manipulations, which allowed us to write down the so-called equation of motion. 2 time derivatives of the position x is equal to minus k over m times x. And all we did is we essentially guessed a solution for x as a function of time. What we realized is that we wanted a function where after we take 2 derivatives, we get minus that function back. And so we correctly guessed that it was going to be a trig function. There was sine and cosine. We used the cosine solution. When you take the first derivative of the cosine, it becomes minus sine. You take the second derivative, the minus sign becomes minus cos. And so their 2 derivatives is the cosine function back again with a minus sign. And that's what we wanted. Our solution was valid as long as this cos omega t, there was a restriction on omega, the angular frequency. In order for our guess to be a valid solution, omega had to be equal to the square root of k over m, which allowed us to solve for the period. The period is 2 pi divided by the angular frequency. And this is what we got for the oscillation period of our mass of spring. Okay, and then what we said, okay, what if we started thinking about a pendulum? Well, we ended up drawing a 3-body diagram. We picked a coordinate system where our y-axis was along the string, and then our x-axis was perpendicular to that. We decomposed the gravitational force into components along the x and y axes. And then when we analyzed Newton's second law for the x direction, we ended up with an equation of motion that looked like this. And so it was 2 derivatives of the angular position, theta, was equal to minus some constants, g over L times sine theta. And that looks similar to the mass on a spring, right? If we could get rid of the sine and adjust a theta there, then that would mathematically look just like the mass on a spring. But that sign makes it a bit different. And so where we ended last time was trying to think about ways that we could relate theta and sine of theta. And so what we ended up doing is we drew a circle of radius r. We identified 2 points on the circumference of that circle, P1 and P2. And so the red line is the arc of the circle that connects P1 and P2. And we realized that that arc length was the radius times the angular displacement between those 2 points. We chose to call that angular displacement 2 theta. So if we take r times 2 theta, that's the length of that red arc. We also thought about the straight line that's connecting P1 and P2. It's this blue line. We ended up making a right angle triangle by bisecting the angle 2 theta. And so half that blue line was equal to r times sine theta. So then the full blue line is twice that, it's 2r sine theta. And it's obvious from looking at this picture that the red arc is longer than the blue line. And so what we could do is we could say, well, that means 2r times theta, the red arc, is greater than 2r sine theta. Now, of course, they both have 2r in them. And so we could cancel those two things on each side of that equation. And we can conclude, therefore, that theta is greater than sine of theta. And this only works for theta in radians. It has to be in radians because the arc length formula, r times the angular displacement, only works when you consider the angle in units of radians, not degrees. Okay, that's essentially everything we did last time. So what I want to do now, to take this a step further, is I want to think about the same sort of comparison, but we'll make the angle 2 theta small instead of large. And so we probably drew this last time as well, but I'm going to pick a small angle. So let's call this 2 theta, where this is now obviously a small little angle. And then we could highlight, the arc, the section of the circumference between those 2 points. And we could draw also the straight line between those 2 points. And, in this case, when we look at this picture, the blue and red lines are not so different. In fact, their lengths are pretty comparable. It's still true that the circular arc is always going to be a little bit longer than the straight blue line, but it's not that much longer. They're pretty close. So the point that I want to make now is that if we consider a small angular displacement, and so let's call it 2 theta between points, instead of P1 and P2, which we've already used, let's say Q1 and Q2. So this would be, say, Q1 would be right there, and over here would be Q2. So if we consider a small angle between these 2 points on the circumference of our circle, then the red arc and blue line are approximately the same length. And this approximation gets better and better and better as we make the 2 theta smaller and smaller and smaller. Okay, so if that's true, then we would say, well, if S is approximately equal to D, we know that S is 2r times theta. That's the arc length formula. And that has to be approximately equal to the length of the straight line, which we worked out to be 2r sine theta. Now, just like we just did a second ago, we could say, well, there's 2r on both sides of this expression, and so we could cancel those. And this argument then implies that sine theta is approximately equal to theta when theta is small. And this is called the small angle approximation. And we're going to make use of this because if we use the small angle approximation in our pendulum problem, then we'll be able to convert this equation of motion that we've been working on into something that looks just like the mass on the spring. Okay, just so you know that this small angle approximation is valid up until theta is around 15 degrees or so. But then of course, you have to convert the angle to always be in radians. So this is valid for theta in radians. Okay, so let's apply the small angle approximation to our pendulum problem. Okay, so let's go back to our pendulum problem here. And if we're going to apply the small angle approximation, all it means is that everything we do from now on assumes that we never displace the pendulum very far away from its vertical. So if this approximation is good up until about 15 degrees or so, once we go beyond 15 degrees, the analysis that we do will begin to break down. Okay, but as long as we restrict ourselves to these small angles or to small amplitude oscillations of the pendulum, what we're going to do now will be valid. So I'm going to call this equation star. We might have labeled it 3 in our notes last time, but let's call this equation star. So in this case, equation star becomes 2 derivatives of theta with respect to time. Now I'll put approximately because we're going to make an approximation, and it was approximately equal to minus, let's look, it's G divided by L. G divided by L. And then it was sine theta, but we're going to make the approximation that sine theta is approximately theta. So right here is our approximation. Okay, now when we compare this to the mass on a spring, these, the symbols we're using are different. Instead of an x, we have a theta. Instead of k over m, we have g over l. But other than that, like, those are just symbols. Mathematically, these are identical. So this is mathematically identical. Whoops. Identical to a mass on a spring. And so for the mass on the spring, it was 2 derivatives of x was equal to minus k over m times x. And then the solution was x was equal to a cos omega t, where omega had to be equal to the square root of k over m. All right. So we know the mass on a spring and its solution. Now we know that our pendulum in the limit of small angles is mathematically identical, and so it must have the same solution. Okay, so therefore the solution for the pendulum angle theta versus time is, well, theta must also be A. Oh, sorry. Must also be A cos omega t, where what would omega have to be equal to? If we compare, sorry, let me put our equation at the top of the side. So compare the mass on a spring to our pendulum, and if omega for the mass on the spring was k over m square root, what must it be for the pendulum? G over L, and all under a square root, right? We can even mentally check the units because little g is a gravitational acceleration. It has units of meters per second squared. We divide by the length of the string, that's going to cancel the meters. So we have 1 over second squared, and then we square root it. So we have 1 over seconds, and that's the correct units for like frequency, right? Okay. Now, omega is 2 pi times frequency, or 2 pi divided by the period. So therefore, the period is equal to 2 pi divided by omega, which is 2 pi, and omega, we just said, was G over L. So for our pendulum, we would say the period is equal to 2 pi, and we could write it as the square root of L over G. And this is valid for small angles. This is a kind of an interesting result because it doesn't have anything to do with the mass that's at the end of the string. At the end of the string, we could put a bowling ball, or we could put a tennis ball, and according to this, the period of oscillation would be the same. It also doesn't have anything to do with how large our displacement is, how large the swing is. As long as we are in the regime where we can use a small angle approximation. So whether we do a 5-degree displacement and then release it, or a 10-degree displacement, or a 15-degree displacement, the period apparently is always going to be the same. Who has some idea of why does the period have to be the same, or why does it turn out to be the same for different amplitudes? Like it has to swing through a longer range of distances for a large amplitude. So how could the period be the same? Anyone have? Yeah. Yeah, that's right. So if we displace it a larger angle and then release it, essentially what it's doing is it's falling a greater vertical distance when it gets back to its equilibrium position. And we know from conservation of energy that if I bring it out to some large-ish angle, it has a relatively large potential energy. And then I release it. So it has large potential energy and no kinetic energy. Then I release it and it swings down to the bottom. It loses all that potential energy, but converts it to kinetic energy, 1/2 mv squared. So it has a lot of kinetic energy, which means it's moving fast. So something with a large amplitude is oscillating with a larger average speed than something with a small amplitude. And so those two effects turn out to compensate for one another. So when you have a large amplitude, you're swinging through a large distance, but you're moving fast. When you have a small amplitude, you're traveling a short distance, but you're moving slow. And those two things turn out to give the same period of oscillation. Okay, so this is something that you're going to look at in labs number 1 and number 2. Okay, good. So maybe we'll make a couple notes about some of these results, and then we'll move on to a new topic, which will begin starting, like the fundamental thing we're going to talk about in this course is electricity and magnetism, and we'll start with some electricity. So let's note that the period of oscillation is independent of both the mass m of the pendulum bob and the initial amplitude of the oscillations. Okay, and so we could say that large amplitude oscillations move with higher average speed than small amplitude oscillations. Okay, good. Does anyone have any questions about this? All right. And so in addition to getting prepared for lab number 1 and 2, this has also been a bit of a review of some of the key concepts from Physics 111. Eventually, when we start talking about charges moving in magnetic fields, we will run into circular motion again. So some of these concepts will be useful as we move later into the course. Okay, good. So let me start a brand new page because we're going to switch topics here. And so now what we're going to start talking about are chapters, well, it's chapter 5, sections 1 and 2 in the OpenStax University Physics Volume 2 textbook. Okay, and so we're going to start talking about electric charge. And, you know, whether or not you took grade 12 high school physics, a lot of these concepts I think will be familiar, but let's just go through them and see how we can understand where these ideas came from. One of the important things in physics that I think is sometimes overlooked is that everything that we try to do to explain nature, it all starts from experimental observations. And so what you do is you do some experiments, you check that they're repeatable, that you can get consistent behavior, and then you try to build a model, some kind of physical model that describes that behavior. Once you have that model, you can deduce other consequences that follow, and then you can start to do more experimental tests to really figure out, you know, how accurate, how reliable is this model. So here's the experiment that I want to think of. We're going to just imagine doing this, but this is something that you could easily do at home by yourself in, you know, a few minutes. Okay, so this is not some abstract thing that nobody could ever do. Anybody could do this. So let's imagine the following experiment. What we're going to do, all you need is some pieces of tape, like Scotch tape. Scotch is a brand name, but it's the cellophane clear tape, very common tape that everybody has. Okay, so we're going to take 2 pieces of cellophane tape. Sorry. and we're gonna stick them together. So cellophane tape, has one side that's not sticky and one side that is sticky. We're gonna take the sticky side of one piece of tape and stick it to the not sticky side of another one. Okay, so we take two pieces of cellophane tape and they're gonna be stuck to one another. And so we'll have the sticky side to non-sticky side. Okay, so that's the first thing you do. And then all you're gonna do is you're gonna pull them apart. So we'll kind of rapidly pull them apart, and then we'll initially keep them isolated from one another. Maybe we have some kind of bar that's set up and we just stick them on the bar so that they're not interacting with each other or with any of the surroundings. Okay, so we pull the pieces apart. And once we do that, we're gonna repeat with two more pieces of tape. Okay, so then what we're gonna have is we're gonna have 4 pieces of tape, and they're gonna be prepared in similar ways. I'll color them different colors just so that we can keep track of their similarities and differences. So let's imagine that I take the first two that are stuck together. Maybe the bottom side is like where we had the non-sticky side in contact. And so we'll label those bottom. So these are prepared in the same way. And then on top of that, we put the sticky side of the top piece of tape. And so we'll call that one top, and then we pull them apart. So the two bottom pieces are prepared in exactly the same way. And then the two top pieces are prepared in exactly the same way. And so two bottom pieces are identical, the two top pieces are identical. Okay, one last step is we're gonna take a 5th piece of tape. This one is not gonna have any special preparation. We're just gonna take it off the roll and then just do nothing to it. And we're gonna call that our control piece of tape. So we're gonna take a 5th piece of tape that has had no kind of treatment, no preparation. This is gonna be our control. Okay, and so I'll color that one a different color, and we'll make it blue, and we'll just call it the control. Okay, so what we have are our bottom pieces, our top pieces, and our control. Okay, so simple enough. And what we're going to do is we're just going to do a series of experiments with these pieces of tape. The first thing we do is we take the two bottom pieces of tape and then we just bring them close to each other. And what we're going to find is that they repel one another. Okay, so observations. The first one is the B pieces of tape repel one another. Okay, then we do the same thing with the two top pieces of tape. We bring them close together. They also repel each other. And in addition to that, the repulsion is kind of the same strength of repulsion that we saw between the two bottom pieces of tape. So the other observation is that the A pieces of tape repel one another. Okay, then what we do is we take a bottom piece of tape and a top piece of tape and we bring them close to one another, and we see that they actually attract, and they attract quite strongly. Okay, Sorry, what did I say? This should be, sorry. So let's fix this. Observations. The top pieces of tape repel one another. Okay, so now we take the bottom and top and we bring them close together and they attract. The top and bottom pieces attract strongly. Okay, and we're going to make one more observation. We still have this control tape that we haven't used yet. So, I mean, maybe one observation that I will not write down, but you could do is we could actually prepare if we wanted two control pieces of tape. And then when we bring them close together, they don't interact with each other at all. So there's no attraction or repulsion when we bring two control pieces together. But then what we can do is we can take, say, a bottom piece and a control piece, and we bring them close together, and they actually attract, but only weakly. Their attraction is weak compared to the attraction between T and B. And then we take a top piece of tape next to the control tape, and it also attracts weakly. Okay, so the control tape C weakly attracts both top and bottom pieces. Okay, and so now what we have to do is we have to come up with some kind of physical model that explains these observations. And so some of it you probably already know. When we pull the pieces of tape together, what we're going to say is that they get charged. And so when we sandwich the two pieces together, overall, everything is electrically neutral, but then when we pull them apart, one of them becomes negatively charged and one becomes positively charged. And so if we have the bottom pieces, say, are the negative charged ones, when we bring two bottoms together, they repel, and so that's like light charges are repelling each other. When we take the two top pieces, those are going to be positive if the bottom ones are negative, and we bring the two positives together, they also repel. But the negatively charged bottom and the positively charged top, they attract, so opposites attract. That still doesn't explain what happens with the control piece of tape, and so let's see if we can figure some of that out. Okay, so we're going to make a model of atoms that form all materials. Okay, so our model is going to be, and again, this is not going to be surprising. We're going to have a dense nucleus, and that nucleus is going to be charged positively. You know, what you know, I'm sure, is that the nucleus is made of protons, which are positively charged, and neutrons, which have the same mass as a proton, but no charge. So in this dense nucleus, we've got our protons and neutrons, and our protons are giving the nucleus a positive charge. Atoms are electrically neutral, so we must have some negative charges somewhere that balance the positive charge of the nucleus. And so the model is going to be a little cloud of electrons that surrounds this nucleus. And let's see, how many protons did I draw? 8, I think. So I should draw 8 electrons kind of hovering around this nucleus in this electron cloud. And so I think that's 8. All right. So what we have is we have a nucleus. Nucleus. That's not right. We have a nucleus. with neutral neutrons and positive protons. Surrounding the nucleus is a cloud of negative electrons. And overall, the atom is electrically neutral. All right. Now, the other thing that we're going to have to know about the atom is that the protons and neutrons are very heavy compared to the electrons. Does anyone know what the proton mass is? Yeah. Yeah, so the protons have a mass of about 1.67 times 10 to the minus 27, I think. Does that sound right? So proton mass, proton slash neutron mass is something like 1.67 times 10 to the minus 27 kilograms. And the electron mass, does anyone know? 9.11 times 10 to the minus 31 kilograms. Yeah. So, 9.11 times 10 to the minus 31 is essentially 1 times 10 to the minus 30. The proton is close to 1 times 10 to the minus 27. So they're different by a factor of 10 to the 3, which is 1,000. So the protons are approximately 1,000 times heavier than the electrons. And the neutrons are also 1,000 times heavier than electrons. That means that when atoms interact with one another or with other objects, it's relatively easy to displace electrons, the light electrons, compared to the heavy protons and neutrons. Okay, so because the electrons are light compared to protons, they can be displaced relatively easily when interacting with other objects. Okay, so that means a couple of things. The first thing it can help us understand is when we had our two pieces of tape stuck together and then we pull them apart, why did we start with two neutral pieces of tape with no net charge, but then we pull them apart and suddenly we have two charged objects? Well, the idea is that one of the pieces of tape had some electrons stripped off of some of the atoms near the surface and transferred to the other ones. And so there was no charge was created or destroyed in that process. All we did is we took some electrons from one piece of tape and transferred them to the other one. So the piece of tape that gained electrons became negatively charged, and the piece that gave up some of its electrons became positively charged due to the absence of electrons, right? The number of protons didn't change, so the total positive charge on that piece of tape remained the same, but it now has a deficit of electrons, and so overall it has a positive charge. Okay, so when the two pieces of tape are pulled apart, some electrons from one piece, could be the top one, for example, are transferred to the other piece, say the bottom one. Okay, the tape that gains electrons becomes charged negatively, and the tape that lost electrons becomes charged positively. Okay, and then from our first two observations, which said that bottom and bottom repel, top and top repel, but bottom and top attract. What we can deduce from this model is if this is all true, then it must mean that objects with a like charge repel and objects with a opposite charge attract. So from the first two observations, our model suggests that one, like charges repel, and opposite charges attract. Okay, so we could draw that as a picture. If we have a positive and a negative, there's going to be some force of attraction between them. If we have a positive and a positive, there's going to be a force of repulsion. And same thing, if we have a negative and a negative, there would be some force of repulsion. Okay. Now, we still haven't explained what happens with our control piece of tape. And that's the last thing that I want to do to finish off today. Just before we do that, it's the same thing that happens, like, I'm sure you've all had the experience, you take a balloon, you rub it on your hair, like I can't do it, but if you have hair, you can do this. You rub the balloon on your hair, and then you put it on the wall, and it sticks to the wall. And so with this model, this friction between the balloon and your hair is transferring, say, electrons from your hair to the balloon. And so now the balloon becomes negatively charged. Your hair is going to be positively charged. So that's why if you hold the balloon still, but not close to your hair, but not touching, your hair gets attracted to this balloon because they have now opposite charge. Then you take the balloon, you take the part that was rubbed against your hair, you put it on the wall, and the balloon sticks to the wall. So it overcomes that gravitational force that would tend to cause it to fall down. So we haven't explained that effect yet. Okay, so when a charged object is brought close, but not touching, to a neutral object, the atoms in the neutral object become polarized. And so we're going to have to explain this term polarized. Okay, so Sorry, you guys have a question over there? Hello, do you have a question? Okay. So what we'll do is we'll draw a neutral object. So this could be whatever, anything. It could be the wall, okay? And so initially, what the wall has is a bunch of atoms that have these electron clouds. And so I'll draw a few of them. And, you know, if there's nothing nearby to disturb this wall, the electrons surround the positive nucleus in a symmetric way. And so for somebody who's far away from this wall, it looks like the wall is overall neutral, which it is. There's the same amount of positive and negative charge. Okay, so now what we're going to do is, so there's nothing nearby. So now what we'll do is we'll have the same wall, but I'm going to take some kind of rod, and we're going to put, say, a positive charge on the end of the rod, right? We take the rod and we rub it with a piece of silk cloth or something like that, so we charge it up. And then we bring that near to the wall. So what we're going to have is, here's our nucleus. Nothing really happens to that nucleus. Those are heavy protons and neutrons. They're strongly interacting with one another via the strong force. And so nothing much happens to the nucleus, but the electrons are light. They're low density in this cloud surrounding the nucleus. And what happens is that these electron clouds get distorted. So the negative electrons are attracted to this nearby positively charged rod. And so we get this distortion of the electron clouds. And now what we would say is, well, the positive charge on the rod is attracted to the electrons in the electron cloud, but it's also repelled by the protons in the nucleus. However, on average, the distance between these distorted electron clouds and the rod is smaller than the distance between the positive nucleus and the rod. And so because that negative charge is on average closer, that force of attraction is stronger than the force of repulsion between the nucleus. And so overall, you have this net attraction between this positive object and this object, which is still, it's still neutral, but the atoms are polarized due to the distortion of the electron cloud. And so that's what happens with your balloon. If you rub your hair with the balloon, let's say the balloon becomes charged positive. I don't know if it becomes positive or negative. Let's say it's positive. I bring it close to the wall is neutral, but the atoms near the surface of the wall, the electron clouds get distorted towards the balloon. And so now there's more negative charge closer to the positive balloon. And so you get that net attraction. The same thing with our pieces of tape. The neutral tape, if I bring a positive tape nearby, the electron clouds and the neutral tape get distorted towards the positive and there's a net attraction. If I bring a negative tape near the control, then the electron clouds get distorted the other way. They get pushed away from the negatively charged tape. Now the positive nucleus is on average closer to the negatively charged piece of tape. There's still an attraction of about the same size. Okay, and so that's the idea between for the interaction between neutral objects and charged objects. Okay, so have a good weekend, and we will see you on Monday.